A huge thanks to my Patreon supporters for making this episode possible. Good morning, fellow mathematicians! Welcome back to another video. You guys wanted it, I'm going to do it, at least a tiny little bit. You know, about my really hard exam series, and all the time I get in the comments, could you calculate through some of those exercises? And I thought, yeah, why not? I mean, we don't have too much group, ring, blah 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 theory here on this channel yet, so why not do some group theory? And today I would like to start off with the first exercise of the Algebra and Arithmetic exam by Professor. Ooh. Okay. So just as a little side note, you can find the link to the exam down there in the description. I have it here for the exercises, and I'm going to solve those questions how I would solve them in real life, in an exam situation. So basically, when you're doing an exam, you basically take everything from the lectures for granted and you are going to make use of it. This is why I'm going to use, for example, Lagrange's theorem to find out the order of some group, for example. So we need to show that UV, that its order is 8, for example. And other various theorems that we have covered in our lecture. So we are going to dive right in. Group theory, it's a lot of fun. And let's first go through the question. The first part of the question states that we are going to have some matrices A and B out of the general linear group of order 2 with the entries from set 3. General linear is just a set of n by n matrices, 2 by 2 matrices with entries in set 3 in this case, where all the matrices are invertible. That is why it's called a general linear group, because there's an identity element in there. All matrices are invertible, okay, just like with each and every matrix. A matrix, all matrices are invertible, and yeah, this is just a general linear group. Makes it a group in itself. Then we have U being generated by the matrix A, which is this, and we have V, which is the group, being generated by the matrix B. And at first, let us show that UV is also, so U times V basically, now snag fell down, is indeed a subgroup of the GL to set 3. You're going to find some outtakes there on the second channel, just because I'm going to go through a lot of calculations. When I do exams, I'm being pretty cautious about everything, and I like to calculate everything through such that I can make sure that everything is nice and correct. I'm going to do the same here, like I said, real life situation basically, and yeah, you can find outtakes, etc. The little uncut versions on the second channel, the trivial channel, not Flammable Maths 2. Okay, so at first we would like to calculate the powers of A and the powers of B, because U and V are being generated by either A or B. And we need to see what order A and B do have in order for us to find out that our UV is indeed a subgroup of the GL2 set 3. So we are going to dive right in. We are going to start with the powers of A. Okay, so there are the kitty caddies, there's the play button if you're new here. Okay, we have kitty caddies on the wall. So A squared is nothing but, it's A times A, obviously. I'm going to write it out for now. 1, 2 times 1, 1, 1, 2. And they are all in the modulus 3, okay? Now, we are going to multiply stuff together. Those put on top of here are going to give us 2, okay? 1 plus 1 is 2. Then we are going to have 1 plus 2 is going to be 3, but in modulo 3, it's going to be 0, okay? Now, next up, 1, this makes 3 yet again, which is going to be 0. Now we are going to put this on here, it's going to give us 4 plus 1 is 5. 5 minus 3 makes 2, so this is 2 in our modulo. Meaning overall, we are going to have a common factor of 2 on all of these entries. We are going to factor it out times the identity matrix. Basically, I'm going to rewrite it using the identity matrix. Now this is what we have. Keep this in mind, this is really useful. So if you ever see something like this, rewrite it using the identity matrix. It's extremely useful, okay, for later purposes, and it really makes calculations easier. Identity matrix commutes, for example, with each and every matrix. Just keep this in mind, it's the identity. Now next up, a to the third power. Now a to the third power is nothing but a times a squared, but a squared is nothing but this. Okay, so this is a times 2, basically in our modulo, times the identity matrix, but some matrix times the identity matrix, just the matrix in itself. Meaning overall, this is just 2 times each of these entries. Meaning overall, this is 2, 2, 2. This makes 4, and modulo 3 is 1. Alright, great. Now we are just going to compute a to the 4th power. And here's where the magic is going to happen. A to the 4th power is nothing but a squared times a squared. This is nothing but this squared. So this makes 4 basically times the identity matrix, but 4 is nothing but 1 in our modulo 3 that we are going to have. So 1 times all the entries in the identity matrix is just the identity matrix in itself. Great stuff. Meaning, after 4 powers, okay, a to the 4th power, we're going to land at the identity matrix. Meaning overall, the order of this group U is nothing but 4, okay? So the order, that's an implication, order of U in this case is 4. Now we are going to compute all the powers of B. Now B squared is nothing but, I'm going to write it out, so this gives us 0, 2, 1, 0, times 0, 2, 1, 0. And just keep in mind, I haven't done this course in like 5 years, so I took some preparations. The last part of this exercise really gave me a headache because I totally forgot all this shit about cosets. But other than that, I'm still pretty good on the topic. I must admit myself. So everything I said in my exam video was kind of improvised. I didn't do any further research at first. So yeah, I really have to say I did a good job there, kind of. Okay. So we're going to compute this. Putting this on here gives us 2, and then putting this on here, 0. Putting this on here gives us 0. Putting this on here gives us 2. That's curious. Does this ring a bell? This is nothing but 2 times the identity matrix, but this is exactly a squared, what we have right here. So also keep this in mind. This is going to become important later, okay? Just because for the elements in UV and how the set even looks like. Now we are going to compute b to the 3rd power. Well, by the same arguments as before, this is nothing but b times 2 times the identity matrix is 2 times b, giving us, okay, on this entry, on the diagonals, it's going to be 0, and then 2 times 2 is going to be 4, modulo 3 is nothing but 1, and 2 times 1 is nothing but 2. Okay, great job. And now we are going to continue. B to the 4th power. You might have guessed it, okay, by the same arguments. It's nothing but b squared times b squared, okay, which is going to be the same as a squared times a squared, which is the identity matrix. Overall, this tells us yet again that the order of V is thus nothing but 4, just like with the order of U. Now, for this next part, to show that UV is indeed a subgroup of this, I'm going to make use of a little theorem, okay, that we have derived in homework before in our course. And for this theorem to hold, we need the orders of our subgroups that we have right here, okay, to be finite. Also, we need U and V to be actual subgroups of the GL2 set 3. They are subgroups because, okay, why are they subgroups? So overall, at first, they are subsets of our GL2 set 3. I hope you agree with me, because all of those matrices are invertible. If you were to compute all the determinants, okay, here it's easy, determinant not equal to 0. Here it's easy, determinant not equal to 0. The determinant here is nothing but negative 2. It's going to be not equal to 0 because negative 2 is the same as 0, 2. On b squared, yes, we had this before, and on b overall we have the same determinant as on here. Same with the determinant here. Determinant is 2 minus 1 is 1, not equal to 0. Determinant of here is the same as with b squared. Determinant here is 2 minus 4 is negative 2, makes 2 yet again. So all the matrices are invertible because the determinant is not equal to 0. Meaning overall, we have an inverse element for each element in these sets. Under multiplication. They are closed under multiplication because if you multiply each and every element together, it's going to be in U and in V yet again. Next up is that we need an identity element. I mean, it's quite obvious that we have identity elements here, and matrix multiplication is associative. So we are done with that. They are subgroups of the GL2 set 3. Now we can make use of this one theorem I have told you about before, okay, or that I have scratched on the surface before. What we want to show with this theorem is that we can express UV as being U times V basically, so generated A times generated B. And with this theorem we can show, so want to show, that we can express UV as a group being generated by A and B. And for this we need those two, U and V, to be subgroups of what we want to show, okay, of UV being the subgroup, this is what we need. Also we need the orders to be finite, and we need that for some K in Z, we have that A times B is the same as B times A to the kth power. And once this last statement holds, we know that UV is going to be generated by the matrices A and B, making it a subgroup of the GL2 set 3. Next blackboard. So my boys and girls, weiter im Text, okay? Let's continue with the text. This doesn't make any sense in English, never mind. So I've written out all the powers that we have here, that we have found out up until now. They are important. A and B in itself are powers themselves, okay? We need this later for UV, how the elements actually look. And now we are going to go ahead and try to see if we can express A times B as some B times A to the kth power for some K out of the positive or negative. No, just out of the positive integers, okay? This already works out nicely. So let us go ahead and get started. A times B, let us see what this looks like. A times B is nothing but, what do we have? So 1, 1, 1, and 2. And also B is nothing but 0, and this was 2, I believe, 2, 1, 0. Now multiplying this together, we are going to get, okay, putting this on top gives us 1, putting this on top gives us 2 it is, putting this on top gives us 2, and this gives us 2 yet again. This is what A times B looks like, and I want you guys to notice that we do not have this element here in our list yet. So we can make sure that it's also in UV, okay? Because UV is probably going to be generated by the matrices A and B in some way, okay? And thus also their multiplication. Now let us check. B times A to the first power. What is this going to be? Well, this is just this turned around. Now I need some concentration. Putting this on here, we are going to get 2. Putting this on here, 2 times 2 is 4, gives us 1. 2, 1, okay. We can already see that this is not equal, but let's see if this is maybe a new element that we do not have here in this list yet. Next up, we are going to take this one, put it on here, 1, and now we are going to take this one, put it on here, 1. It's not equal to this one, okay, it's not equal to AB, but it's also not something that we have yet in this list. So this is good, it's also part of UV in some way after it's being generated. Now, B times A squared. What is B times A squared? Well, remember that A squared is nothing but B squared. So this is just B to the third power, and well, it's definitely not equal to A times B, because B to the third power is something that we already have here. So no, it doesn't count. There's an X behind it. Now, B times A to the third power. That's the only option that's really left for this to hold, because A to the fourth power is already the identity matrix, would make it B yet again. So B times A to the third power is nothing but B times A squared. So this is why I have rewritten A squared originally like this, because it's extremely helpful. So this is B times A squared, so 2 times the identity matrix. B times A is nothing but this, and now all the entries multiplied by 2. This gives us 1, okay? And then all the other entries are 2. And this is exactly what we were seeking. B times A to the third power is actually nothing but A times B, meaning with this theorem that we have shown in the homework back then, we can actually say that UV is thus a subgroup of GL2 set 3, because the orders of U and V are less than infinity, they are finite, they are both subgroups of the same thing that we have here, and yeah, our interchange relationship does hold, with the interchange relationship being this A times B being equal to B times A to the kth power. So we have done that. We have shown the first part, and it didn't take too long, to be honest. And it was already nicely written. Okay, it kind of counts as a proof. Okay, maybe in an exam you would be more careful with the notation and everything, but overall we have found out the main points that are important. Now next, the order of UV is 8. Now, order of UV is 8. We are going to use a variant, so like a Schlussfolgerung from the Satz, from Lagrange's theorem. I'm terribly sorry. Eine Schlussfolgerung des Satzes von Lagrange. It's just something that follows from Lagrange's theorem. Now we can express the order of UV if all the conditions that we had before hold, that like UV is a group because it's a subgroup, thus it's also a group, it's of finite order, etc. We can use this variant of Lagrange's theorem. UV can be expressed as, so the order of UV, the order of U times the order of V, divided by the order of the intersection of U and V. Now we need to find out what the intersection of U and V looks like. What is the set exactly? Well, we just need to see which elements they have in common. Well, at first we have that, well, a squared and b squared, they are in common, okay? They are 2 times the identity matrix. Okay, a to the third power can be expressed by b, okay? Not gonna happen, but we have the identity here. Meaning the order of this thing is 2, there are 2 elements in there. Meaning overall, order of u is 4 times 4 over 2, okay? We can divide by 2, it's not equal to 0. Trusting the Peano axiom, successor of 1. This makes 16 over 2 is nothing but 8. Meaning overall, the order of UV is indeed 8. And thus, we are done with this. Next up is the next exercise. That was easy, wasn't it? The next exercise is, taking a look at the exam yet again. We want to see if W, which is being expressed by the generator of a squared, okay, it's the group, subgroup, whatever, being generated by a squared, is indeed a normal subgroup. At first, let us take a look at the order of W. This is going to be important for the last part. Okay, order of W is pretty easy to compute because the order of A is 4, meaning the order of A squared is thus 2. Okay, so squaring A squared is going to give us A to the 4th power as the identity. So we have that the order of our W is nothing but 2. Like I said, it's going to be important later. Now we need to show that W is a normal subgroup. For W to be a normal subgroup, we just show that either W is the center of this group in general, so it's the center of UV, or we are just going to show that it's a normal subgroup in general. This is kind of easy to show. Now I need to think about everything. So we have, for example, so U, so those are the elements in UV, times some W, so those are the elements in W, times U to the -1 is yet again in W, I think. Maybe there's an annotation there. And this holds for all U in UV and for all W in W. We have that this holds. I hope this is correct. This should be correct. If not, there's going to be an annotation. We are just going to show this directly by taking a look at the 2 elements, put them in here, and see if this actually holds for all the elements in our UV here. They are actually all invertible. Okay, that's what we have found out before. All the elements in here are invertible. You can check this yet again because we have 2 new elements. This is invertible. We have 2 minus 4 is going to be a 2 yet again. And the same should be here. So all elements are invertible. Same should be here, 2 minus 1. I'm going to see you on next Blackboard. That's a lot of writing. Let us do this quick. So, all the stuff we have done before, successful, pretty great. Video is going way better than expected. No second take here to do. So next up is we want to check for all the elements in W. Let us check for, okay, A squared is at first. A squared is nothing but 2 times the identity matrix. So for A squared, which is 2 times the identity matrix. What are we going to have? We want to check that for all the elements in our UV, we have that, if we multiply this stuff together, okay, so with the left and the right elements, it's going to be in W yet again. So we are going to take some random arbitrary U out of our UV, multiply together with 2 times the identity matrix, then multiply together with U to the -1 power. I mean, that's a pretty cool thing, right? I mean, we can bring the 2 to the front, it's a scalar, doesn't matter, and the identity matrix times some other matrix, I mean, it's just a matrix in itself. So this results in 2 times U to the -1 power. This is going to be the identity matrix. And this is yet again in our W. I mean, it's just a squared, all right? Works out pretty nicely. Now next up is a to the 4th power, which is the second element in there. Well, this is nothing but the identity matrix, and you might have guessed it, U times the identity matrix times U to the -1 power. It's going to be U times U to the -1 power is just the identity matrix, which is indeed W. And thus we are done. It's an enormous subgroup, isn't that amazing? Next up is the last exercise, the one that gave me a bit of headaches because I didn't know how to handle this coset stuff anymore, okay? Has been a while, 5 years ago almost, okay? We are going to dive right in. We want to show that UV in the factor group with W is isomorphic to the Klein 4 group, okay? And I have said something wrong in the exam video. I said that the Klein 4 group is the cyclic one. No, it's the one that is not cyclic. Meaning we need to show that each element in here, okay, so at first we need to show that both have 4 elements. Klein 4 has 4 elements, and for them to be isomorphic, you can also write isomorphic with this equals to isomorphic thing. They need to have the same cardinality, the same order. So we need to show it first that UV in the factor group with W it has indeed 4 elements. This is one thing that we need to show. This is pretty easy to show because this statement just implies that the order of UV divided by the order of W is 8 over 2, it's nothing but 4. Okay, coolio, works out, that was easy. And we also need to show, since the Klein 4 group is not cyclic, that the factor group is also not cyclic. What does it mean for a group not to be cyclic? We need to show that there is no element in here that has the same order as our factor group in itself. So no element in there must have order 4. Okay, that's what we need to show. Here's where a lot of calculations will come in, a lot of outtakes, because it's kind of a lot of calculating, okay? I'm going to go through each and every thing that we are going to have here and then see if any double, and then we are going to see what the elements explicitly are in our factor group. Just as a side note, what is the factor group exactly? UV, factor group W, is nothing but, well, it depends on your operation. We are having matrix multiplication here. So this is the set of all U times V. So times the set V in itself, where U is element out of UV. Okay? And then U times W is exactly all the sets in here where U is out of UV and our W is out of W. Okay? So just keep this in mind for all the calculations that we are going to have. I'm going to give you the first example. So U times V. Okay, we are going to find out all the variants here. So we are going to take an element out of UV. Let's say we are going to take A. Okay, do you know what all the elements in our UV are? Those are those 6 elements, and A and B. Okay, we are going to take our A. So A times W is going to be exactly the set of A times the first element in here of W. So A times the identity matrix, which is nothing but A. Okay, and also A times the identity matrix times 2. So 2 times A. Okay, just as an example. This is A times W. We are going to do this with all 8 elements because we have 8 elements here in UV. And then we are going to see what the elements actually are that we are going to get in here. Meaning overall, our factor group looks as follows, our quotient group. The factor group is nothing but the set of, what do we have? We have identity times W, we have A times W, we are going to have b times w, and we are going to have ab times w. And now all that's really left to show is that none of these elements in here have the order 4, okay? This is all that we need to show. There's one important thing that we are going to make use of here. We are going to make use of the fact that if we have a to some power times w, since w is normal, this is the same as a times w to the kth power. Just saying. So we are going to raise everything to the 4th power here, and we are going to show that this is indeed not equal to our identity. Okay, we want to show that's not of order 4. This thing, or we are going to show that all of those have order 2 or order 1. We are going to do it like this, not raising it to order 4. That would be it would be the same argument. We are just going to raise everything to the 2nd power, and then we are also done with this. The identity matrix times w is trivially of order 1. I mean, it's the identity, basically. So this is already done. Order 1. So now we are going to have a w squared is equal to a squared w, but a squared w is nothing but 1 times w. So the identity times w, meaning this is of order 2 because we landed after raising it to the 2nd power at the identity matrix. So this has order 2, this has order 1, okay? Now b times w is going to give us b squared times w, but b squared times w is the same as a squared times w, which is identity times w. Order 2, we are done with that. Now a squared, b squared times w. Here's where some fun comes in, okay? B squared is nothing but a squared, gives us a to the 4th power times w, and a had order 4, okay? A had order 4, meaning overall this is going to be the identity matrix times w. After raising everything to the 2nd power, we landed at the identity, meaning overall all of those elements have order 2, none of them have order 4, meaning it's not cyclic, and thus we are done with le exercice. I hope you did enjoy this video. If you did, please like, subscribe, recommend channel if you like, okay? This was a lot of fun for me. That was quite something different, but I would love to do more of this. Group theory is a lot of fun. It's just so nice and abstract, and it's such a lot of fun. There was a lot of calculating, but I hope you still did enjoy this. If you want more of this, feel free to let me know down there in the comments. Also, there's soon going to be content up on Flammable Maths 2. It's going to be about numbers overall, N, Q, R, Z, etc. And yeah, check that out, subscribe to the channel. I'm until the next video. Have Flammable Day. Also, new logo merch just dropped. It looks fantastic. That's the Conscious collection. Check it out. Link will also be in the description. Ciao. Love you guys. Appreciate ya.
Jetzt filme ich ihn, wie er sich seinen Lümmel ableckt. Na toll.